Hi, everyone. So this is probably going to be a fairly short continuation of yesterday. I mostly want to talk about tunneling, but before I do that, I want to drop a few comments regarding yesterday's lecture on scattering. So maybe this didn't come across, but here you have these three regions, right? Region 2, Region 1, and Region 3, where the potential energy looks like this, right? And we discussed that here you have an incoming wave, A e to the I kx. Well, I think I call it K1. Then you have a reflected wave, the net reflected wave, B e to the I K2x. And then you have a transmitted wave, E to the I K1x. Sorry, this is K1, not K2. And then there's stuff going on inside. There's wave function inside, but I'm not writing, right? This is only the spatial part. There is also the temporal part, e to the minus I omega t, that I'm not showing those temporal parts. And so this corresponds to the scattering state where the energy is above the potential energy. We discussed transmission coefficient, which is the physical meaning of which is the probability of transmission. And that's E squared magnitude of E squared over magnitude B squared. So, sorry, A. Folks, I'm very tired. I'm misspeaking a lot. Like that. And in general, this is less than 1, but it's close to 1. And there are several values. They're actually kind of a resonance conditions when you get perfect transmission. It's a type of resonance. What I wanted to say is that these coefficients, E, B, A, they're generally complex. So, for example, the coefficient E has a magnitude and it has a phase. Okay, it has a phase, and it's the magnitude that enters the transmission probability. What matters is the magnitude. The fact that it has a phase, what it means is that it basically just adds constant phase offset to this factor. So you could write this. So you could write this whole thing. You could write this whole thing like this. So it's a phase shift. And in general, these phase shifts are necessary in order to meet those boundary conditions. We didn't discuss the phase shift. I just wanted to mention. But the fact that transmission probability is generally less than 1, what that means is that here's the amplitude of the incoming wave. Here's the incoming wave, sorry, not the amplitude. Here's the incoming wave. Right, so this is this region, and the outgoing wave will have the same wave number because region 1 and region 3 are the same, but it will have a smaller amplitude or magnitude. So here's E and here's A. And the same thing can be said about the reflected wave. It generally has a smaller magnitude, a smaller amplitude than the incoming one, that A. So that's what I want to say, that the fact that transmission probability is less than 1 in terms of these waves, it means that just by definition, it means that the magnitude of this magnitude, the magnitude of this outgoing wave is smaller than the magnitude of the incoming wave. That's precisely what it means to say that T is less than 1. So in general, we have waves, but they all have different magnitudes or amplitudes. And they also have phase shifts relative to each other, but we didn't discuss phase shifts. I just wanted to make this clear. I think it's supposed to be pretty clear anyway, but just wanted to bring it up explicitly. The second thing I wanted to say is that, well, in general, scattering is much, much more complicated than 2D. Here's the basic idea. It carries over from the 1D discussion. You see, in 1D, we just have probability of particle reflecting and probability of particle transmitting. That's it. In 2D, there's probability of particle going this way or this way or this way or this way or this way, back scatter, forward scatter. So if you have some kind of a scatterer, and then you have an incoming particle. So this is an incoming plane wave, incoming plane wave, right? Just like this guy with amplitude A, magnitude A. This plane wave gets scattered by the scatterer, and some of it scatters back, okay? So this is the analogy. So this is kind of like the transmission, and this is kind of like the reflection. But in 1D, it's clear. Reflection means back, transmission means forward. In 2D, we don't really make that distinction. All it is that you have some kind of an incoming wave, and then you have the result of that incoming wave interacting with the scatterer. And the scatterer could be some atom or a glob of atoms, or some kind of a potential energy defect. If you shoot a wave packet, right? So you have some kind of a wave packet that you shoot, right? Again, it's really in 2D. In 1D or in 2D and 3D, it's pretty complicated. There will be a time when the wave packet reaches the scatter, and in general, it will be very complicated, complex dynamics. Imagine waves hitting a rock in the ocean. You have like pretty complex dynamics, but long after the time when this wave packet interacts with the scatter, long after you have some kind of an outgoing, outgoing wave. So this is, let's say that this is before, and it's impacting the scatter, and then long after, what you would have is, this is after, this is supposed to be the same object. Long after, you have some kind of a product, the result, some kind of a result, okay? A wave packet comes in, it interacts, it's a very complicated dynamics, and long after you have some kind of a residual wave. And what happens during the interaction can be very complicated scattering of waves. Just wanted to say that about 2D and 3D. I recommend you read your textbook. I noticed that your textbook doesn't discuss this situation, but it does discuss this situation. And the reason it does is that because doing that allows it to discuss both what happens when energy is less than the barrier height and what happens when energy is bigger than the barrier height, right? So I'm going to talk about this now for the case when energy is bigger than the barrier height. Sorry, less than the barrier height. When energy is bigger than the barrier height, qualitatively you have something similar to this, like what I discussed yesterday, but the formulas are a little bit different. So if I assign you a problem about this bottom situation for when energy is bigger than the barrier height, you just look up the appropriate formulas in the textbook, okay? Please do that. So the textbook does not discuss this, but for scattering states, I'm sorry, for the states when energy is bigger than the barrier height, it's qualitatively similar to the bottom case that the textbook does discuss. But I would like now to talk about this situation for when the energy is less than the barrier height. So this will lead us into the discussion of tunneling, and I'm not going to do much math. The pictures, you get the idea for how to do this, right? So this is tunneling. So why is it called tunneling? We'll see in a moment. So Here's our potential energy graph. So actually, before I talk about square wells, square barriers, let's go back to physics. Physically, you might have some kind of potential energy like this, right? So you might have a potential energy as a function of distance. Classically, it says that there's a force to the left. So the force to the left of x naught is pointing to the left. That's what I'm trying to say. Minus of the slope, right? So the force is pointing this way, and here the force is pointing this way. So if there's a particle that's coming in, it will be slowed down. And as long as the energy is below the top of the potential energy barrier, the particle will stop at the turning point, and there's a force at that point, so it will immediately turn around, right? So this is the turning, classical turning point. And that's it. So the particle will arrive, momentarily pause, and go back. If its energy is like this, it cannot penetrate this barrier. I told you that you can think of this potential energy graphs in your mind's eye in order to develop the intuition. You can think of them as actual physical landscapes. So if this is an actual, imagine sled, you know, I push the sled up this hump, up this hill. The potential energy is actually equals to mg times the y, right? So if this is the vertical coordinate as the y, the potential energy as a function of x mimics the shape of the hill. And so to say that your energy is below the height is equivalent to saying that your sled will stop at the point, and it will stop at this coordinate when all of the energy, it will go to some height, right? So u equals mgy will go to some height, and at some critical height, it will exhaust its energy. It will exhaust its kinetic energy. Kinetic energy is 0, and then it will turn back. It will not go over a hump, right? So this is a gravitational example, which is very vivid because the potential energy landscape mimics the geographic landscape. There's just a constant of proportionality, mg. Okay, so I really encourage you, especially in one dimension, I really encourage you to think about this kind of a hill-valley analogy. But don't forget that it's really a one-dimensional. There's a little. I'm cheating a little bit because the sled actually moves in 2 dimensions. When you have, so in general, it's really 1 dimension. So in 1 dimension, this really corresponds to a particle experiencing some kind of a force field. Particle stops and goes back. Just like when we talk about the parabolic potential energy, it really corresponds to, for example, it corresponds to this. There aren't, the mass doesn't actually go up and down. The mass just goes left and right. But you can imagine what that mass will do if you imagine placing a little cart, and the cart will go, will oscillate around the middle. So that's this mnemonic trick that I'm advocating, right? So, but of course, remember that really it's only just a motion 1D. Okay, so I think you get what I'm trying to say. So the particle comes, stops, and goes back. And if we have something artificial for the purpose of making it easier for us to calculate, you have something artificial like this. Let's say the potential energy graph. So this is more realistic. And this is a model. We do a lot of modeling, right? So the potential energy graph is like this. Well, this sort of a situation now corresponds to like this. It's kind of artificial, but what this means is that the particle moves uniformly at constant speed, stops, and then goes back at constant speed. It will never penetrate into region 3, right? So now I can label my regions. I could even do it in the realistic one. Okay. If the energy is above the well, then it will move fast, then slow, then fast. That's what your textbook discusses. And that's qualitatively similar to what we discussed yesterday. But if the energy is below if the energy is below the maximal potential energy barrier, then classically the particle will just never penetrate the barrier. What's happening quantum mechanically? Well, quantum mechanically, what you have is, well, again, on the left, you have minus h bar squared over 2m psi double prime equals E psi. So this is minus 2m E h bar squared. So this is the wave. Now I'm just going to call it K. And similar here. So this is region 1, region 3. So it's the wave function. Remember, in quantum mechanics, we deal with waves. What's waving? The wave function is waving. The particle doesn't have this shape, okay? So when we started talking about wave-particle duality, the students immediately started trying to visualize the particle is doing the snake thing. No, 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 okay? Be very careful with your imagination, because your imagination is a classical imagination. Wave function is the key to the particle. Psi 3. And what goes on in region 2 is you have minus h bar squared over 2m psi double prime plus u psi equals E psi. So psi double prime equals to the u minus E times h bar squared over 2m psi, right? And you see that this is a positive quantity. U minus E is a positive quantity. I'm going to call it kappa squared, okay? I think your textbook maybe calls it alpha or something like that. Okay, so it's E minus U, and then there's a minus sign. And then continuing, you know that here the solution is going to be, again, it's some kind of incoming wave plus some kind of an outgoing wave. Here it's going to be a linear combination of growing and decaying exponential. And here it's going to be, again, a linear combination. In general, it's going to be a combination of left and right moving wave. For scattering from the left, we're interested in solution where f equals 0. And so then we will relate B to A and E to A, just like we did yesterday. And we will define the transmission coefficient to be like this, and the reflection coefficient to be like this, okay? By the way, the obvious thing that I forgot to say yesterday is that there is a transmission and reflection coefficient for any energy above U naught. And so what that means is that you have a solution for any energy above U naught. So for the bound state, when energy was below U naught, so right, so we looked at this kind of situation, the bound state, we had solutions only at specific values of energy. For the scattering state, any energy you give me, sure, there is a solution. And as you change the energy, the relative amplitude of E and B will change. And that's why the transmission and reflection coefficient changes. And when energy is extremely high, oh, by the way, sorry, don't confuse E with energy. When energy is extremely high, the coefficient E is almost identical to the coefficient A, and the coefficient B is almost 0. In other words, the amplitude of the outgoing wave is almost the same as the amplitude of the incoming wave, and the amplitude of the reflected wave is very small as you lower energy, right? As you consider incoming particles with a smaller value of kinetic energy, well, the amplitude of the outgoing wave will be a little bit smaller and the amplitude of the reflected wave will be a little bit larger. So there is a solution for any energy above the well, and depending on the energy, the relative magnitudes of E and B change. And the same thing happens here. Okay, the same thing happens here. So the first obviously interesting fact is that T is non-zero. You can have transmission in this situation. Think about it. You can have transmission where classically it would be impossible to do. The energy is fixed. The energy is not jumping up or down, right? You're not borrowing energy from anything. But the transmission happens because there's a finite probability for the particle to go through the barrier. And this is called tunneling. So if I may reproduce the barrier picture again. So this is your potential energy as a function of position. So here's the energy well, or it's an energy barrier. It's not a well anymore. And we're looking at this kind of situation. So the wave function has some kind of a amplitude A. In this region, it will be a combination of growing and decaying exponential. It's not a purely decaying exponential. You need both terms to satisfy the boundary conditions. But if the barrier is deep, I'm sorry, if the barrier is high, if E is much larger, is E much less than U naught, this is U naught, the coefficient C, the growing part will generally be very small. So it's technically a combination of growing and decaying parts, but it's approximately, it's mostly a decaying part. That's what I'm trying to say. It's mostly decaying. So you have something like this. Let me do this. Okay, so, and then there's some wave function left. Right? So this wavelength is the same as this wavelength. So the wavelengths are the same, or K and K. The wave numbers are the same, but the amplitudes are not the same. And ooh, what's going on here? And generally, E is less than A, and typically much less than A. So if the barrier is wide, most of the wave function will have decay. The barrier is tall in comparison to E, the wave function decays faster, because remember that the rate of decay is the square root here. Kappa equals rate of decay or growth, but again, the coefficient in front of the growing term is typically smaller than the coefficient in front of the decaying term. This will be given by this quantity, which is just a second. Just a second. Let me make sure I got this right. I didn't. Sorry, folks. I messed up here. I could sense that I messed something up. So it looks like this. I think it should be 2m over h bar squared. Right. So therefore, I could sense the something slippery going on. 2m of h bar squared. And so you can see that if u is much greater than e, it will decay faster, right? So the rate of decay will be larger. And if u is not much larger than e, if u minus e is not as big as if it was bigger, then the rate of decay is smaller. So there's more wave left after the barrier, right? So on the other hand, let's say you keep u and e, but you make the barrier wider. Well, the wave function does decay. So as you make the barrier wider and wider, there's less and less of the amplitude left. So E can be small either for E can be made smaller and smaller either as you make barrier wider and wider, or as you keep the width of the barrier and you make it taller and taller while keeping the energy constant. Long story short, you get a situation that looks like this. There's still going to be some amplitude left. And this process is called tunneling. Let me make this a little bit prettier. Something like this, right? So generally, something like this. This process is called tunneling. Poetically, people say particles go through walls. And I guess they're thinking of something like this, right? The sled example. If it was a quantum sled, it means classically you come to some height and then you go back. But quantum mechanically, you find yourself on the other side of the hill. That's probably where that's probably where the terminology going through walls or going through barriers come from. It's only poetically correct. In practice, it means that, well, you can find a particle on the other side of the barrier. Again, this is just the very basics, the essence, where I'm shooting a plane wave in one dimension against a square barrier. Realistically, you have some kind of a smooth potential energy landscape. You probably will not be shooting a plane wave, you will be shooting a wave packet, and you probably will be doing this in 2D. But this captures the essence of the effect, that it's possible to have a transmission in a situation where classically you would not expect it. Classically, you would expect transmission coefficient to be exactly 0, the reflection coefficient to be exactly 1. By the way, I guess I should give you a formula for the transmission coefficient. Just a second. It's stated in your book. I will not go through the derivation, but the transmission coefficient for quantum tunneling in 1D against the square barrier has this kind of a functional form. Your textbook gives it to you in a slightly different algebraic form. I will simplify it a little bit further. So this is now energy. So unfortunately, I'm using E. This is not energy, this is coefficient E. So not energy, but this is, let me use this, right? So this is better. Plus U naught times, sorry, this is a minus, there's a minus sign. Times sinh hyperbolic sine okay. By the way, sinh of x equals e to the x minus e to the minus x over 2. Just like sine of x, e to the ix minus e to the minus ix over 2i. Just a little math trivia. And so if you plot this transmission coefficient, let's say starting with energy equals 0. So if you plot the transmission coefficient, you get up to u naught. It will look fairly unremarkable. It will be just some kind of a function that grows. And when E equals to u naught, the transmission coefficient will not become 1. The transmission coefficient reaches a certain value, which is 1 over 1 plus u naught over a quarter. So that's just an interesting result. As E goes above u naught, well, the transmission coefficient continues to increase. So that's not tunneling anymore, right? So this is tunneling. This is tunneling. Right? So in this situation, your energy is below the barrier. When energy is above u naught, now working in this regime, and it's similar to yesterday. You still get reflection and transmission, and you still get these kinds of resonances. I guess this is going to be 1. You still get these kinds of interesting resonances. And your textbook gives you the value of energies at which the transmission coefficient hits a 1, those resonances. Very similar to what we discussed yesterday. And your textbook has a graph that basically looks like this. So this is interesting. This is a process called tunneling. And you would say, well, this is cute, but why do I care? So a lot of nuclear processes happen because of tunneling. I will ask you to read section 6.3 on alpha decay and some technological applications. They talk about something called tunneling diode. It's a type of diode that uses tunneling. I think they also talk about superconducting quantum interference devices. It also uses tunneling junctions, some kind of superconducting junctions that use tunneling. But in general, so if this is, we discussed this kind of a nuclear potential energy graph, right? So this is the potential energy of a nucleon, like a proton interacting with the rest of the nucleus. And we talked about the classical, so for example, if energy is like this, then the classical motion is such that, let's say you shoot a proton, it would come to a stop, reach the turning point and go back, and we'll never see it again. And vice versa, if it's inside, it will be able to get to the turning point, but it will not be able to escape. Tunneling allows the completion of both, tunneling allows the proton from outside to end up inside, even though its energy would not allow it classically. And it also allows the proton to escape from the nucleus, even though classically it would not be able to escape. And this is kind of how radioactivity works. So application to radioactivity. Radioactivity. In radioactivity, it's not a single proton that gets chipped away or tunnels away, but it's an alpha particle, a helium nucleus. So basically bits of a nucleus tunnels out. What remains is a smaller nucleus and this tunneled bit, which is a helium nucleus, also known as an alpha particle. So radioactivity works basically because of tunneling. And certain nuclear reactions can be accommodated by tunneling. So I will ask you to read section 6.3 about applications. And that's really all I wanted to say today. I think we're done with chapter 6. It was just yesterday and today. Some highlights. I encourage you to read the textbook because it gives a complementary discussion. It has very nice discussion of applications. And I just wanted to mention some highlights. And that's all. Thanks for your attention.